All right, let's talk about metamorphic rocks. Metamorphic rocks are kind of the rock that gets skipped over a little bit, but they're really important. Metamorphic rocks are an incredible resource when it comes to mining operations. They're one of the biggest resources when it comes to hard rock mining. So let's talk about them really quickly. Now here's your refresher. All right, so one thing we like to think about with metamorphic rocks is what is the protolith, or the rock that was before. All right, so the protolith in our case that we're going to start with is a shale. So what happens when you take a shale and you increasingly heat it and bury it? Right, you were to heat up a shale to say 250 or 300 degrees, you would start to get it to recrystallize a little bit and turn into a slate. And so if you take a shale and a slate next to each other, you thump, thump, thump on the slate, it's going to have a really high ting, ting, ting noise, but the shale, the unmetamorphosed shale, is going to have like more of a thuddy noise, because what's happening is just like when you fire a pot in the oven, you're recrystallizing everything in the slate, and it's crystallized and glued together. And so it makes that harder tinging noise because it's almost porcelainized of all the clay that's internal to the rock, right? You keep heating it up and keep adding pressure. What you're causing the rock to do is be able to reorient the minerals that are present, flatten them, right? They're regrowing perpendicular to the way you're squishing. So if you're squishing this way, everything's going to start to lay flat and grow larger, and you start to move from the slate world into a phyllite. Now with a phyllite, you're not going to be able to see visible grains necessarily. You might get some big grains growing in there, but you start to pick up a phylitic, what's called a phylitic sheen. It's almost shiny a little bit, right? The ground mass is starting to grow. The rock's starting to become increasingly deformed. Ultimately, you start to see the ground mass, the finer grain ground mass, and that means you've moved into the schist category, all right? The aluminums that are in all those clays are starting to reorganize and grow into micas and chlorite. Those are what's happening in the schists. You might start growing garnet. That's going to be consuming your aluminum, your iron, calcium, and all that fun stuff, manganese, all right? And as you continually heat that rock up even further, you'll start to develop it into a gneiss. And what that means, when you start developing a gneiss, that means you have such temperature, you're talking 600-700 degrees, kilobars of pressure. So you are tens of kilometers deep into the earth, and there's so much pressure that it is causing the minerals to try to link and grow next to other shaped minerals, similar shaped minerals, because they can grow next to each other and kind of get volumetrically tighter in there, packed in there a little tighter, right? And the temperature allows a lot of these chemical reactions to occur really quickly. And so we take the shale, we bury it, cook it, we kind of, just like when you fire a pot, if you're doing pottery, turn it into a slate. A little bit more, you restart growing those crystals a little more, you turn it into a phyllite. Higher temperature, bigger grains turn into the schist, where you have this really well-developed schistose fabric. And then ultimately with the gneiss, you start to pick up banding, because everything is starting to grow next to other similar shaped things. Now, not all rocks kind of have this beautiful increasingly higher grade components. So if you take a limestone and you metamorphose it, it's kind of a one-stop shop. Doesn't matter what temperature you get it to, it's turning over to marble. It does get a little more complicated than that, because if you get a marble hot enough, it will start to volatilize some of the carbonate material in there, and you can get some other reactions, but that gets a little more complicated. You start cooking a limestone, you're ultimately going to turn it into a marble. If you don't stop that, it can move into another realm that we'll kind of leave for an advanced petrology class to cover. Sandstone doesn't. You take a sandstone, you start cooking it where it recrystallizes together, it turns into a quartzite. It has no other recourse. Once it's a quartzite, that's done. You can keep burying it. It will just be a quartzite until you heat it up enough for it to melt. That's just what it's stuck at. Now, basalts are cool. I don't actually like this figure here, but basalt, you bury it, you metamorphose it. Some folks might start to call it a metabasalt on its way up. So as you're recrystallizing some of the basaltic material, might start calling it a metabasalt at some point. A little bit more, it'll turn into what we call greenstone. It's green. That's exactly what that looks like. If you keep burying that greenstone, increasing the temperature and pressure, they've given you a normal schist here. This is not at all what a basalt would look like if you metamorphosed it to a schist grade. Because you wouldn't have that many micas. That's just the quick version. What you're more likely to do is generate what's called an amphibolite. So all these minerals are recrystallizing into an amphibole-rich metamorphic rock, which we call an amphibolite. You keep going, ultimately that can easily turn into a gneiss, right? So everything kind of can make its way to gneiss. Now granite is, that's the only option for a granite, because a granite crystallizes at high temperature. It's kind of used to high pressure. All you can really do is take it, increase the temperature and pressure from where that granite crystallized. In fact, you might be at a similar temperature to where the granite crystallized, but that increased pressure will allow the minerals to move around and form those nice bands, because they're trying to get in the most low volume state in response to the pressure. When we start looking at metamorphic rocks, there's a lot of terms that you probably haven't heard before. And so this is one that I like to introduce because it does pop up on some exams, called microlithon. What a microlithon is like a chunk of a pre-existing rock. And so an example, this fabric here where that yellow line is a pre-existing part of the protolith. And so that's classified as a microlithon. It can actually even be just something from a previous metamorphic rock. If you've metamorphosed a rock once and then you do it again, the microlithon would be something that pre-exists. Or it could be something from the original rock before, the sedimentary or igneous rock that existed before. But that microlithon is going to be a pre-existing feature. All right, so speaking of pre-existing features, something you'll also see when you start metamorphosing sedimentary packages is something called a stretched pebble conglomerate. So these are really cool. What's happened to give you this stretched pebble conglomerate is the rock has gotten to a temperature where the matrix around the pebbles has lost all of its strength, all right, and it is very squishy and is moving around. The pebbles have started to lose their strength too. And so if you can think about smearing those pebbles, you get this elongation of the pebbles, flattening and elongation of the pebbles because of that stress and because of the weakness of the matrix around it. You can get these stretched pebble conglomerates to form. Now, speaking in a similar way, where you have two different strengths within the same rock, if you have a very strong, competent layer, weak layers above it, they're just moving around and that more competent layer wants to stick together. But let's say if you have some extension, and what we'd call this is layer parallel extension, where this more resistant or stronger, more cohesive unit is being pulled less than the stuff above it, but you have extension parallel to the fabric or the layering. That's why that's called that. You get this really cool fabric called boudins or boudinage. The fun little fact, the way to remember that is French for sausage. If you're from Louisiana, that would be boudin, or if you're from the, I guess, Gulf Coast, that boudin is a swamp way of making sausage down in the American Southeast. But same thing, that word comes from the French because it originates out of Louisiana. But boudins are like strings of sausages is the way they're supposed to look. And that's where the term comes from. But it comes from that more competent layer that's pulling apart with big chunks staying resistant, where the upper and layer components have lost all rigidity and are just kind of moving and getting squished apart. With metamorphic rocks, we really like to hone in on what are called kinematic indicators. Which way is the fabric flowing and moving? And now flowing, it's not molten, or it's solid, but it's moving like a plastic. So which way are these rocks flowing plastically, solid state, but how are they moving in which direction? Because that can tell us which way fluids are moving. It can tell us which way blocks of rocks are moving along nearby faults. It can tell us a lot of information, but we have to be able to read these kinematic indicators. And so two of them right here, these are two of the more common ones. One's called a sigma structure, and it looks, I don't know, it looks kind of like that right there. There's your sigma structure, and the way I remember that is, imagine you were to take a block and then shear it, or like a deck of cards, all right? And if you pushed this way on this was a deck of cards, you sheared it that way, you would get the deck of cards to look like that, okay? The other structure here that we need to talk about, the other structure here is called a mica fish. Now, mica fish kind of look a lot like a sigma structure, and if you can imagine, it's the exact same thing. This is tops to the right, right? It looks like it's kind of been sheared over towards your right. So both of these are what we would say tops to the right when we're trying to describe these features. And they're moving over like that. That would be tops to the right, sense of shear, or the kinematic indicator here from these two features here. Another feature that's a really important one, called a delta structure. The way I remember these is I think about like a hurricane. So if you imagine how a hurricane is rotating and kind of put your fingers on top to indicate some of that rotation, you can kind of think of it spinning. You would get the same. This would be tops to the right in the exact same way. You can also see that this tail kind of pulls out and becomes very similar to those sigma structures that we just looked at. But this would be called a delta structure. All right, so let's talk about foliation. So foliation is any planar fabric that we get to develop in a metamorphic rock. In this case right here, you can see the early development of some banding. So this is just kind of getting real close to that schist, nice transition. Depending on where you look, you might get both, but we have other things, not just schistosity, that's our schist fabric development, not just our gneissic banding, but also the cleavage. And so if you remember cleavage, which way minerals break, that's what we learned in mineralogy, that's what we learned in our 100 level classes, but there's more to cleavage. Rocks can break in certain cleavage planes just like minerals. It's not really the same reason why, but we still get these cleavages to develop within a rock. So a good example here, axial planar cleavage. If you were to fold a rock, you can get this alignment of cleavage that is parallel with the axis of a fold. That's called axial planar cleavage. Right here, this picture is called pencil cleavage. And so what happens is you've got a bedding plane and you cause compression in one direction, you can get perpendicular development of that cleavage. So when the rock starts to naturally break apart, it breaks off into these long, square, little pencil-looking shapes, and that's where you get that pencil cleavage or pencil weathering that's really common. All right, schistosity. So we're stepping it up a notch. Schistosity is the development, medium to coarse grain, schistose or planar fabric that's developing in a rocks. The most obvious place you're going to see this is in the alignment of the micas or amphiboles. Now, micas are going to be flat, amphiboles are going to be more elongate or prismatic, sometimes acicular or needle-like, but they're all going to develop somewhat along that schistose plane that develops in the rock in response to the additional fabric there. So you can see there's a bit of a fabric. It's kind of located, we're looking down onto it here. If you use your imagination, there's a lot of amphibole in that. So we're looking down onto the schistose pattern. That's why it looks kind of flat and platy. The next step up is gneissic banding. All right, so just like I told you a minute ago, you have the temperature to drive chemical reactions, but you're trying to reach that smallest volume state. So what the rock is trying to do is get as dense as possible, and it does that by having, say, the feldspars all grow next to each other, and then having all the mafic minerals grow next to each other because they're going to have similar shapes. So think about all of the micas and amphiboles, kind of flatter things growing together, and then a layer of plagioclase, squarish shaped things. All right, they can pack in there tighter. And so this would be the same as if I gave you like a box of golf balls, a box of basketballs, some golf clubs, and a couple like tubas. And I said, try to pack these all together in the same spot. You wouldn't be able to pack them in there as volumetrically small and efficiently as if you were to pack them all individually. All right, everything can pack in tighter next to things of similar shape and size. And so that's why the banding is starting to develop. The temperature is driving it, but the pressure is causing everything to want to get to this minimal volumetric state. Right, the pressure can also drive these things too. These are called pressure shadows. So imagine if you're squishing on something and you have this really hard mineral. It's the little cubic mineral in the middle, all right? And it's not doing anything. It's strong and resistant. But when you're pushing on the sides, you're creating this pressure that's focused on the top. And so if there's any sort of material in there that can go into solution under that pressure, it can. In fact, the pressure is driving it to go into solution. and it moves over to the sides. And then it comes out of solution around the mineral or around the microlithon or whatever is holding that everything together, and it precipitates out along the side because that's lower pressure. The pressure was causing it to go into solution. Once it gets on the sides, it is able to drop out of solution. A good example of that you'll see even in sedimentary rocks are called stylolites. Stylolites are pressure solutions that are in limestones. And so you have a limestone, you have a lot of pressure, enough temperature for everything to get dissolved. Everything will leave, and what's left is the remnant non-dissolvable component that was in that limestone, and you get these really cool squiggly lines, and those are stylolites, but those are pressure-driven dissolution. All right, another really cool feature that we'll see pretty commonly are called crenulation cleavage. So when you start folding up a rock, particularly like phyllites and higher grade slates, you'll see the rocks start kind of folding, and when the folds start getting closer, they start to develop these cleavage planes. You can see almost where looks like the wrinkles are lining up, right? Every one of these is a little fold wrinkle, and then they're starting to kind of line up. And when they do that, they create this really well-developed cleavage in the rock that is called the crenulation cleavage. And so when we get that, we have now two things we can measure. One, we would call it our S1, our schistose fabric, that is the major schistosity. But we have another planar fabric, which would be our crenulation cleavage, that we could also measure. Now we also get lineations, and these are kind of hit or miss. Sometimes you'll have a lot of lineations in metamorphic rocks, sometimes you'll have less or so. But a lot of times, this example looks like a bunch of amphiboles have started to align. One, they're flat, parallel with schistosity, right? They're aligning parallel to schistosity, but they also look parallel in a mineral lineation fabric within the schistosity, all pointing that way, right? So we can also have stretching lineations similar to the stretch pebble conglomerate, but in this case, the minerals grew in that orientation to give us that linear fabric. And so that gets us to a new term called tectonites, right? And so when we have rocks that have clearly had some sort of flow fabric that is preserved in there, remember these are not this is not magmatic, these are not molten, these are still solid rocks that are starting to ductily move around. They're starting to flow as a plastic. When that happens, you start to get these tectonites. There's really two different things to a tectonite. One's called an L tectonite, lineation. One's called an S tectonite, which is the schistose. You can have an LS tectonite, which has a little bit of both. All right, in this case, here's an example. If you look on the top, you can see there's kind of round mineral features up on the top, so it doesn't look like a schistose fabric, but you look on the side here, you can tell those have been stretched. So this is a classic L tectonite, where you have this unidirectional stretching. The rock has been smeared out. That's a wonderful example of an L tectonite. You can see that edge right there. Up underneath is, see up underneath right there, you can see they're more planar fabrics. Up on top, you can see they're kind of flat, right? This is a really nice schistose or S tectonite, where everything almost looks flattened, looks squished. But over right here on the right, you're going to get a little combination. Everything looks like it's been flattened on this front side just a little bit, but you can see along the side that you definitely have that linear or L tectonite fabric that is very strongly developed on that side over there. All right, so those are all things that we're looking for when we look at metamorphic rocks. Are we looking for stretching? Are we looking for pancaking, flattening? Are we looking for old chunks of things left, the microlithons? Are there any kinematic indicators that we can pull out of these rocks and use to figure out which way things are moving? Those might directly correlate to faults or directly correlate to folds or other transportation if we can get those sense of shear indicators or kinematic indicators. The other part we start looking for, and this is really critical in mineral exploration, is piecing together the history of the rock. And so we piece together these things called pressure, temperature, paths, PT paths. In fact, you really want to play it pressure, temperature, time, because we want to know through time how these rocks are moving around in the crust. How's the pressure and temperature change through time in the crust? And this is really important because certain temperatures, certain tectonic events, These rocks need to be in the right place at the right time at the right temperature for mineralization to occur. So if you're in economic geology, these pressure, temperature, time paths are really critical to trying to find the right rocks that were in the right place at the right time. So how do we calculate the pressure and how do we calculate the temperature? There's a couple ways. The most common way to do it is we rely on reactions that are pressure insensitive to give us the temperature, and we rely on reactions that are temperature insensitive to give us the pressure. All right, here's an example. Stick with me. We know garnet and biotite both take in iron and magnesium. And what they do is they exchange that iron and magnesium based on the temperature. So if we can get a chemical analysis of the garnet and a chemical analysis of the biotite, we can do some nice fun chemistry math and figure out what theoretical temperature they equilibrated at. That gives us a temperature. We can use a very similar approach to figure out a more or less what pressure the rock equilibrated at. And so if we have a pressure estimate and we have a temperature estimate, we can figure out where that rock was at that time. Now within a rock, let's say we're able to do that in the core of a garnet. Maybe there's a little bit of biotite included in the core of the garnet. We can also do it on the edge of the garnet. Maybe there's biotite right in equilibrium with the edge of the garnet. That gives us two spots. We know the core started first. We know the outside, the rim of the garnet was later. And so then we have two places that we knew that rock had to go through, two temperatures, right? And we can do that again with different mineral assemblages. In this case, we can also take the whole rock and say, all right, we're going to take this rock. We're going to look at the whole composition of it. And we're going to get what's called a pseudosection, right? This is a theoretical mineral assemblage at all pressure and temperature options. All right, so what this does is it goes in and it does an estimate for what the lowest Gibbs free energy mineral assemblage is at each pressure and temperature. All right, we can take that rock and then look at a thin section and identify all the minerals and find the field that matches. That has to be our peak assemblage where this rock equilibrated. So now we have maybe a estimate on where the garnet started growing because we have the core, maybe where the garnet stopped growing, that's the rim, the peak assemblage of the rock, that would be this field, and that would constrain what we call our prograde garnet path from lower temperatures and pressures to higher temperatures and pressures. And if we can go in and get some geochronology with radioisotopes, we can put numbers to this. That is what we'll use to correlate to any sort of larger tectonic event, magmatism, whatever. We can also do this on the way out. So in this case, we have an estimate down here of where we think the garnet started growing. Those compositions tell us the garnet started growing down here, 650-ish degrees C, 6.5 kilobars of pressure. We know it had to go up, kind of swing through this dark field here into the red. So it kind of had to counterclockwise hook back. That hook back is the rock post-metamorphic cooling off and then probably coming back out. That would be called as retrograde path, right? Prograde is its peak conditions. Retrograde is how it gets back up to the surface. All right, again, very important if we're trying to look for mineralization because we need that timing. Now, if we don't have numbers, the other thing we can play is what's called pre, syn, and post. Is it pre-kinematic, so pre-deformation, syn-kinematic, during deformation, or post-kinematic? Did it occur after deformation? So same thing's true. If we're looking at a gold play in one place and we find that the gold vein emplacement is post-kinematic, all right, we can go start looking at other veins and trying to piece that same story, looking for more post-kinematic veins, right? We think the gold emplacement event might be post-kinematic. That's what we're looking for. And so being able to tell these things apart is very important. Here's an example. This pre-kinematic means you've got this little chunk, this bottom left. When the deformation event occurs, it overprints everything in there, right? Because it was pre-kinematic. It had to exist beforehand. We take that same chunk, post-kinematic, it grew over the fabric. That's what they're trying to show with this image, right? So it's growing over the fabric. In this case, the fabric developed around that mineral. All right, this up here, this little square guy, they show those fabrics up and down, and then they show the sense of shear top to the right. What they're trying to show here is that this thing developed its first little fabric and then was rotated. All right, so that would be its pre-kinematic state. This kind of swirly situation here, they showed that it developed some of that fabric during deformation. That's why it's considered to be synkinematic. And then they are showing you here this thing overgrew the pre-existing fabric. Therefore, that's the interpretation of what that would look like if it was post-kinematic. All right, so these are just 3 mineral growth things that are trying to show you. But veins can also be pre, post, and synkinematic. So like a pre-kinematic vein will now, if a vein were to shoot through some rocks and then be smeared during its ductile flowing, it would just be incorporated as a kind of smushed out, long, linear, smooth feature that has been incorporated as the rock flowed, right? So synkinematic might have some of that smearing, whereas a post-kinematic vein might kind of wiggle all over the place and go up and down and cut through the fabric. That would be post-kinematic because it's cutting across everything.